Okay, everyone. So now you can hear me as well. I want to wish you very welcome here to this Netnod meeting, the first one of 2018. I'm happy to see that all of you found your way here. I mean, this is after all a new venue or a old new venue for us at Netnod. We moved here to Sheraton instead of Marriott Courtyard that we have been the previous years, because it's a little bit more central, it's a little bit better room, and I hope you also see we have a very good and better agenda. So, welcome everybody here. First of all, I would like to take this opportunity to thank our sponsors. Without them, we wouldn't have this meeting. It wouldn't be as good speakers, it wouldn't be as good talks. And I want to thank all of the sponsors here. They all have stands out there. Please go out, talk to them, and see if they have some good equipment that they can use. We use equipment from some of these sponsors, and it's really good stuff. What are we doing, and what are we doing at Netnod? Yes, we are still doing rock solid internet services, and we continue to do that. We also brought one of our rocks here that we have out in the foyer as well, so we can show off that, because it's rather boring to show off infrastructure services that just works, because it's usually not noticeable. It should just work. We have a short update from me, and I'm going to present a little bit on the team. We have two new managers in the team. It's Matthias Arnberg and Matthias Karlsson. Arnberg and Matte, who is taking care of the technical department at Netnod. Arnberg joined us in the beginning of the year, taking care of architecture and development. And Matte Karlsson has been here for a while, but since the beginning of the year, he's taking care of the engineering. I wonder if you both could stand up and wave. So if you have any technical questions, take a moment to speak to one of these two gentlemen. Both are called Matthias, and we sort of, it's Arnberg and Matte. I usually just call them M&M. It's sort of an easier way to know them. You also have noticed maybe that Patrick Feldström is not here today, and he used to be titulated head of development and engineering. He's still around. He's not, well, he actually is on a warm, nice island now, because he's in Puerto Rico at the ICANN meeting. We asked ICANN to move the meeting, but they didn't want it because it clashed with this one, and yeah, so he had to go there. He's the technical director of Netnod, taking care of strategy and the big technical questions and the long-term plan and everything. So he's still around, even if he's not here today. With that, you're not going to have to listen to me anymore. I will hand over to my colleague Martin to give you a brief update on where we are with the business.
Thank you. So, also glad to see you all coming to this meeting. We're looking forward to 2 nice days with lots of talks and interaction with each other. I will give you a short business update, what we are doing on the IX and on the DNS side. My name is Martin Eriksson. I am responsible for all sales and customer relations. And as you know, we run exchanges in Stockholm, which is the biggest exchange. We also do Copenhagen, Gothenburg, Sundsvall, and Luleå, and we recently started up a cooperation with a Norwegian exchange. So we call it Netnod IX Oslo, powered by Nix. And we recently have seen the first customers coming in from our side into Nix, so we see a good opportunity to grow even further in the Nordics together within Norway. Some short statics. We have aggregated traffic around 1.5 terabit. We have, for the moment, 2,500 G-ports overall, and we added 12 of them during the last year, so we see a good growth. We have 7 resellers for our remote peering program. I think at least three of them are here today. It's Reten, Enter, and Portlane. So if you are interested in remote peering and not present in Stockholm, you can go visit and talk to them. In Copenhagen, we also see see good growth of traffic, and we adding more and more of the CDNs into Copenhagen. We have a mix of the networks. I should say about 30% is Swedish, 36 other European. We have 10% of the networks is coming from Russia, which still is a very important market for us, and the other is other internationals. So we have a very good mix of the networks. Besides the IX, we also provide DNS services, where we have about 70 plus global DNS locations worldwide. And we are growing steadily and offering this to both TLDs and partners and enterprises. We have seen a good growth in the service and added more and more resellers to this platform. And we will continue to expand this further. Some news. We haven't updated the pricing. It's valid from today for new customers joining. We will in the future talk about monthly fees instead of annual fees. And I would like to highlight this pricing, and we have a discount that we're working with, which is 40% on the second additional ports, on the highest available speed, which is for the moment, it's for the 100U ports. So if you are interested in this new pricing, please come talk to me or some other of the Netnod guys here. Also, the Norwegian exchange has recently updated their pricing. And in Copenhagen, we have seen a trend with, among other exchanges, to hand away free ports. So we thought we couldn't be any other than them. So we tried this for a short period. So we give away 6 months for free if you connect as a new network in Copenhagen. And this is to add more networks and even grow Copenhagen bigger. So with that, I would like to hand over to Rob Allen, who is our moderator today. And I hope you all will enjoy this meeting, and hope to see you all at the social tonight. Okay, thank you.
Thank you, Martin. So good morning, everybody. My name's Rob Allen. I'm a communications consultant and moderator, and I'm very happy to be moderating this 2-day Netnod meeting. We have a very packed agenda over the 2 days, and it'll be my job to steer us through that agenda, the question and answers, getting us safely to the coffee breaks, the lunches, and of course, the most important thing of all, getting us away on time for the social this evening. Just a quick bit of housekeeping before we begin. Any of the speakers today, 10 minutes before the session in which you speak, if you could go to the back of the room to get mic'd up, our wonderful sound guys will give you one of these delicious radio mics so you can feel like Britney Spears. Also, another piece of housekeeping, in the sessions when we have the questions and answers at the end of each presentation, we're going to have some mics in the audience. Could you put your hand up who's going to be holding the radio mics? There'll be one at the front, and there's going to be one at the back there. So if you have a question, please raise your hand, wait for the mic to come to you, and then if you could state your name and affiliation into the mic before you ask your question, that would be good. Final piece of housekeeping, the buses for the social will leave at 5:45 sharp. Okay. So that's all from me for the introduction. We have a very packed agenda, so it's going to be good to just get going. I'm going to introduce the first speaker of the day. He is Jan George, the Operational Engagement Program Manager from the Internet Society. He works on operational initiatives to ease the deployment of IPv6 and other technologies. He's also working to help the industry document best current operational practices to improve operator feedback to the IETF. He founded the Go6 Institute, aiming to raise IPv6 awareness in Slovenia. And he also was one of the co-authors or lead authors of RIPE 501, which is the RIPE Best Current Practice document for V6 ICT equipment. But today he's going to be talking about another RIPE document, that's RIPE 690. So I hand over to Jan.
Thank you. Hello, everybody. My name is Jan Žorž. I come from Slovenia. I work for Internet Society. And today I would like to talk about something that is not an ISOC thing, as Peter would say. It's a community document. How it all started. I'm traveling a lot around the world, talking to many operators around the world, asking them why they are so slow in deploying IPv6. And when I see the pattern, the generic pattern of a problem that they are telling me, then I say, okay, we should respond, we should write a document that is answering this problem. That's how RIPE 501 and RIPE 554 started, for the operators to be able to request IPv6 requirements when they're buying the equipment. That's how RIPE 631 started. That is talking about how the help desks should troubleshoot the IPv6 problems when people calls in. And then after some time, I heard people saying, okay, what is the prefix that we should delegate to our end users? And people around the world were guessing. They were saying, we should do /64, we should do /48, we should do /56. What should we do? And when I heard this question many times, then I decided, okay, let's put together a good group of operators, of good IPv6 experts, and let's answer this question. So what I will be talking about is basically a community document that we as a group of authors became basically just the humble editors from all the feedback that we got back from the RIPE IPv6 working group and the wider community around the world. So, who in this room is the operator and is busy implementing IPv6 right now? Show of hands. Okay. After in a coffee break, I would be eager to hear from you how you decided on your prefix delegation to your end users. But what is this document all about? Actually, if you make the wrong choice at the beginning when you're deploying IPv6, if you choose wrongly what to delegate to your users, you might have problems later. And you might have to redo everything from the scratch. As you see, these are the co-authors. There are some really, really good IPv6 experts. I was happy to put these people together. You see many people from, for example, Andrew Alston from Liquid Telecom. That's the biggest operator in Africa. We have Slovenian Telecom. We have lots of good people here. Okay. First of all, I would like to thank Internet Society to let me me work on this in my work time, because this is not directly ISOC related. I'm sure you will hear in these 2 days more about Internet Society. I hear they're very busy with manners and routing security stuff here in Sweden. But let's get back to this document. This is a table of contents. As you can see here, what we are discussing here is the number 4 is where it gets interesting. This is the sign of end user prefix assignment. Is it /48, /56, or something else? And then we go into numbering the one link. How should you number the one link? And then we go, should you go /64? Should you go unnumbered? Should you go with unique local addresses? Then we go into v6 prefix out of the IPv6 prefix assigned by the end user and the summary. Then we go into the prefix assignment options, and we discuss about, should we go /48 for everybody? That's my personal favorite. Should we go /48 for business customers and /56 for residential customers? Should we go with prefixes longer than 56? Don't do it. And considerations for cellular operators. And then we come to the interesting part. When people get confused, usually, should the prefix that we assign to the end user be persistent, or should it change over time? And here where things get interesting, because operators tend to learn from IPv4, but also tend to bring bad behavior from IPv4 into IPv6. And that's not good. That's not the way of doing it. So here we discuss why not persistent assignments may be perceived as easier. Of course, you put up your BRAS or whatever you have, you put IPv6 pool there, and then you leave to equipment to assign it as it wants. It's much easier, but is it good? Well, here we figured out it's not. Then we discuss why not persistent assignments are considered harmful, and why persistent prefix assignments are recommended. So, I will not read you the whole document, but this is just the generic set of recommendations. IPv6 is not the same as IPv4. In IPv6, we don't count IPs. We have prefixes that has their own type of usage. /64 is one LAN, is one layer 3 domain. /56 is for something else, /48 is for something else, /32 or /29 is the assignment to the LAR. We don't count numbers. You should not be concerned by exhausting IPv6. You will not exhaust it anytime soon. So if you need more space, go back to the RIR and they will give you more space. RIPE will happily give you more space. So I've seen many people doing their address planning, and usually they fail 3 or 4 times. Don't be afraid to fail. First time, they make it very packed and they don't use much addresses, and then they figure out they did it wrong. Don't be afraid to just throw it into the bin and do addressing again. And then I usually see people making the address planning quite relaxed, and then they exhaust their IPv6 space, and they go like, okay, we are not going back to RIPE NCC and ask for more space. And then on third time, they make it right. Don't be afraid to break some glass. If you want to make it easier for you, consider this. My personal favorite is /48 for every customer. Lots of also other organizations are considering this as the safest option. It works well. It makes your routing table quite simple and easy to organize. I've heard concerns about this, but basically mostly from sales and marketing people. And they say, oh, now we are differentiating between our business customers and residential users. And we are giving business customers more of resources than to residential users. And we're like, well, yeah, technically there is no need to do that, but if you really want, you can give /48 to business customers and /56 to your end users. And then they go like, okay, if that's technically feasible, then we are going to do this. It's quite easy. There is always a trade-off, but my personal preference is /48 for everybody, and then it's much easier to do. You need to understand that there is a specific case for cellular phones. Mobile phones, if you decide to go on IPv6 only for your mobile phones. The PDP-v6 context that you establish, usually /64 is given to every phone. So that's a little bit different. All right. The one links. If you don't want to get into trouble with troubleshooting, you should not consider using ULAs or unnumbered links on the one, but use the global unicast addresses on your one links to connect your CPEs to your core network. Why? Because if prefix delegation fails, then you will be able to troubleshoot from the CPE, from the customer, towards your network. If you don't give the number to the one link, then your troubleshooting may get messier. Yeah, there is also a consideration for /127 for each point-to-point link. That's perfectly valid if your equipment supports it. But please consider reserving /64 for each customer and just use /127 for the one link. This makes it much easier for everybody. Okay, non-persistent prefixes. Why are they considered harmful? I'll tell you a story. For example, Liquid Telecom in Africa. They started deploying IPv6 for many customers in Kenya, Zimbabwe, and things like this. And then all of a sudden, my friend that is responsible for that there comes over Facebook chats and goes, oh, I'm having problems with Google not serving me Quad A's. Wow. Why is this happening? And then I asked him, did you deploy your IPv6 with changing prefix delegations to your customers? And he said, of course. I said, I told you not to do it. He said, well, I did. What is the problem? What happened actually is, for example, in Kenya, there are lots of power outages. If you have been to Kenya, you have experienced the power outage every day, basically. So what happened was, when there is a power outage, the CPE does not remember the previous prefix that was delegated to this user. And you have a laptop sitting on your network at home. You have IPv6 address that is from the prefix that was delegated to you, and you're trying to communicate with the internet. Power outage, CPE reboots. After CPE comes back, it gets a new prefix. And because the CPE is not aware of the previous prefix, it doesn't send the array packet with lifetime 0 to basically discard the old prefix on the network, but starts just advertising the new prefix. And your laptop gets the IPv6 address from the new prefix. But according to the Murphy's law, that one is not used. It still uses the old one. So what happens is, you try to access Google. You send a SYN packet. And this packet finds its way, because of default routes, to Google. Google sends you back the ACK packet. But this packet never comes back to you because there is no route back to you. There is no, the old prefix is not valid anymore. And Google is then expecting the SYN ACK from you. But it never gets the SYN ACK from you because you are communicating from the old IPv6 address. What happens? They're measuring that. If they don't get the SYN ACK packet from you, they mark your network as broken IPv6 implementation, and they stop serving you Quad A records. And these people was in panic. I explained them this. Look, this is what you're actually doing. If you don't have the CPE that remembers the prefix delegations over power outages, and after it comes back, if the prefix delegation is not the same, start sending array packets with lifetime 0 as crazy to the network, then you're having a problem. And what they did was they needed 3 or 4 days to reconfigure the whole network, and they did basically static prefix delegations to all their users. So this is the recommendation. If you don't have the control over your CPE, and if your CPE vendor did not implement the function to remember prefix delegation over power boots, then do static. If you really know what you're doing and you're sure that things would work, then you can go dynamic, but reconsider things. Oh yeah, this was the authors of this document. This is Andrew. He's from Africa. He was the one having problems, and why we included this part of the. So as you can see, the editing of this document was quite relaxed. But I'm really happy because majority of stuff here also came from the community. We received lots of comments, feedback from the community, and I'm really happy that it got so wide consensus that we can consider it a really best current operational practice. Here are the acknowledgements. As you can see, many people was involved in this document other than the co-authors. And here is where you can find the document. It's free, it's yours. If you want to use it, use it. It's really the best current practice. What is the future work and ideas? We're thinking about a document that is talking about how to run your mail server on IPv6, because I've heard lately when I'm asking operators around the world why you're not running your email on IPv6, and they go like, anti-spam mechanisms are not there, there is no IP reputation mechanism to prevent people from sending me spam. How to survive on IPv6 because spam and things like this. So we thought about writing the best current operational practice on this topic. So if you are running your mail server on IPv6 and you have some operational experience in that, come and talk to me. We are now looking for the group of the authors and people who would work on that. And with that, are there any questions?
So we have quite some time. So if there are any questions for Jan, you have him available here. Anyone operating? Yes, Marco, please, in the middle there.
Oh boy.
Thank you, Marco Groninger, NCC. It was actually a question to you, Rob, or basically to the room. How many people have read this document, and how many people have actually sort of applied the recommendations of this document into the network? I'm just curious to see how far that's been taken here. That's
a great question, Marco. So can we have a show of hands, number of people that have read the RIPE 690? Okay. I'd say that was 10-ish at a rough count. What was the second part of the question, Marco? Sorry.
Whether they applied it to their network.
And so of those of you that have read it, but hands up one more time, the people that have read the document, sorry. Okay, so for those of you that have read it, keep your hands up. If you've applied that document, please keep your hands up. Okay, a few hands went down. Okay.
Okay, it's just the generic recommendation. It's not set in stone, but it's basically the lowest common denominators. What we heard from operators that they are doing and survive in deploying IPv6. You need to. I need to emphasize, deploying IPv6. It's not hard. the decisions while deploying IPv6 sometimes are hard because we are thinking with IPv4 in mind. And we are writing these documents to make it easier for you to do some decisions. You know, and I'm happy when in the document, after it closes the editing cycle, it comes from the community something that sometimes I even don't entirely agree, but you know, if that's the will of the community, if that's the feedback from the community, who am I to argue? So this is basically the completely community feedback and the advice. Okay, there are no other questions, so I will just...
Any more questions for Jan? No?
Nope.
Well, thank you.
Very much.
Please join me in thanking Jan.
Thank you.
So we're running quite early this morning. Before I let you go for a very early coffee break, just one other announcement. You might want the printed agenda for the Netnod meeting. If you find that helpful, you can find them here on the front desk for the printed agenda. And with that, we'll break early for coffee, and we'll come back at 11 for the second session. Thank you. Hello, everybody. Welcome back to the second session of the Netnod meeting. I hope that you enjoyed your extended coffee break, but I guess that this is Sweden, so no one's going to complain about some fika. So the first speaker for this session, I'd like to introduce Christian Adel. He works with DevOps and network engineering at Schibsted Products and Technology, where his main focus is providing network services over heterogeneous IT environments. And that's what he's going to be talking a bit about today, which is multiple platforms, one network. So Christian, could you please welcome Christian to the stage?
Thanks. Hello. I'm really happy to be here today, just to share with you my learnings. This will be a presentation about some learnings that I have done through a design process just to create a network service. So, as the presenter introduced, I'm working for Schibsted. Schibsted Media Group is based in several countries, around 20 countries across the world. Here in Sweden, probably you know about Blocket and also Aftonbladet and other media houses. And the presentation here today will be a journey and also a love presentation. A love story about how network engineers and developers can work together, creating useful services for both worlds. Sometimes this is difficult to achieve. I have been working as a traditional network engineer for almost 10 years, until I decided that I had to move to a more full-stack approach. I need to get some skills that I was lacking at that moment, and I decided that the way to go was move to a new company and start from scratch on this way. So all these learnings, all these design decisions, success and failures will be presented here today. Let's start with a short recap about networking, because it's like the leitmotif or the aim behind this story. Present how a DevOps approach or a more automated way of doing things can be useful for the network industry. I'm not going to go through all the challenges that probably you know, but internet scale technologies and applications are driven a change on how we operate networks. So this focus on scale, focus on velocity, against the traditional reliability concept that the network industry has, is changing the way that we operate the networks. And this traditional network approach sometimes is not good enough. So the question that probably some of you have done, and I did to myself some time ago, was if we were ready for this change. If we look into our networks, we can see that sometimes we have multi-vendor networks, sometimes with legacy devices. And if you go to understand which are the difference when you work with legacy devices, for me, a legacy device is a device that the interaction is designed first as a human interaction. If you, as an example, probably you know about an open source project, Napalm. If you go into the code and you go to the different modules, it's completely different how looks a Cisco iOS from a Arista EOS, for instance. Why is the difference? One was designed just for interacting with machines, the second one, and the other is for humans. So the scrapping of the configuration for the same function you get from 3 lines, that is just a get and a JSON parsing, against a scrapping of the lines is completely different. So it makes a big effort to automate these things. Also, going to this way of automating things gives you a lot of opportunities to learn, but sometimes it's also a blocker for you, because there will be a lot of things, not just a few new protocol behavior or functionality. There is a lot of things to learn, and also it's a challenge. The trainings, usually networking, has been really focused on learning things about protocols. If you look, for instance, into the CCII curriculum, you will see that these topics that I'm going to present today are less than 10% of the topics. So we are more focused on the protocols itself, that is a really important thing, but we are not focused on how to operate and handle it accordingly. Also, some fears that I recommend to think about is the automation. amplifies your success, but also your failures. So you could be some kind of afraid of automating things, and a failure impacts in your infrastructure and in your reliability. There are some things to mitigate. I'm going to also to introduce today. And finally, and it's an important thing that at least is my experience, that sometimes network engineers are so far from the developers. And the developers are the ones that are creating business logic and creating value to the company. So if we keep far from them, we are not having the impact that we can get. As an example, I remember working in my previous company that network engineers were in a different building than the developers, not just the different room, different floor, a completely different building. So communication was not the way to go there. And having all this in mind, sometimes it's difficult to start because you have so many things to do that it's complicated to start from something. How we can approach it? I'm not going to go through these specific things because all the presentation is about these, not buzzwords, it's just ways to do things. So starting from working with APIs, business machine-to-machine interaction, to just going through coding skills, iteration, this stuff that makes possible to create things in an agile way is the way that we should start thinking in networking. Without leaving the idea of everything should be reliable, we should start thinking on creating network services that are closer to the applications. So the presentation itself that starts here, and you should expect a demo that, as usual, could fail, but hopefully the video is going to work as expected. I'm going to introduce a network service. And why is it important for a company as Schibsted to have a network service? You can see this as an IT ecosystem nowadays, that we are not only based on on-premise, so a service can be distributed across several platforms. Imagine platform A as an on-premise data center, platform B, another data center, platform C, a public cloud, platform D, another public cloud. So you have several networks distributed, and the service is distributed across all of these. This is what an enterprise company looks like today. And the network is something more similar to this. It's a bit exaggerated, but at the end, what you get is a multiple relations between these services that if you're in a data center, you can implement with a VLAN, with a VXLAN overlay network, whatever you have. If you're running in a public cloud, you can get a specific peering technology, or if you have to interconnect several networks in different platforms, you can run a VPN tunnel, an overlay, or just going through internet. The question here is that there are several technologies. It's nothing impossible, but the most difficult thing to achieve and to interconnect is the different people working with these technologies. And this is what is really difficult to achieve, because there is people operating these services that has some knowledge, and other people have another knowledge, and making these things work together sometimes is difficult. So this model, that is the current one that we have in Schibsted, and we try to improve, has some downsides. The first one, and I think that is the important one, is that by default, what you get is that the services interconnect through internet. Through internet is the default way to connect, but it's not always the most performant way to connect. You can get an internal link that has more bandwidth than going through internet. Also, it's not the most secure and not the cheapest one. If you have to, you usually pay for the traffic that you move to internet. Either on your infrastructure, on your premises, to your ISP, or to your platform cloud, you get the same. Also, related to the manual operation or traditional operation, going through a manual process to handle everything is difficult. Difficult to achieve the speed that you are demanded. Developers are used to work with networks, with services that are created on demand, and the network has to follow this. So you cannot say that we will create the connection next week or tomorrow. The connection from different services has to happen at the time that is demanded. Also, you work manual, there are some errors that could happen. Manual provisioning could mean some errors because following procedures is not something that always happen the same way. And finally, some communications still need some network layer security. Hopefully, most of the applications are running security at layer 5 with SSL or TLS, but there is still legacy applications that still need some kind of network tunneling. So we try to solve all in one, some kind of squad team of network security engineers, basically people with some network knowledge, meet together almost 3 months ago and came up with this cool design. So it's quite easy. It's not rocket science. It's just what it's known in AWS world as transit VPC, that basically you have several platforms, could be public clouds, whatever, or on-premises, and you, instead of communicating service to service, you create a virtual router service wherever you want to place these routers, could be in the cloud, on-premises, wherever you want, and running some kind of standard technologies like VPN, IPsec, and BGP to routing as a routing protocol. You distribute the routes from one service to the other. All this together, you can just create a central point, define a scale-out architecture, so you can just grow as you want in this place, like a leaf and spine architecture. We also think on how you operate this network, so we just define an automation process using Ansible to create the configurations, go through analysis process, getting the NetFlow information from these routers, take decisions, and add some kind of logic. So you could see this logic part as a SDN flavor. And we tested this with several routers, vendors. I remember Cisco, BIOS, Arista, and it worked perfect. It was a nice technical exercise. And we came up with this solution. We also tested different VPN architectures. So we tested also the DMVPN. Instead of going to this central point, this is only for routing, for control plane, and we did the data plane here. So we came up with this solution to the upper management, really happy that this is going to solve everything. And this was the result. We failed it. And the failure that we get was really something useful for us, because we learned a lot of things, and things that most of them are not technical, but are things that if you want to operate a service that has to run quickly and evolve as the business or developers want, you have to think as they do. So you have to understand what they really need, not what do you expect that they will need. You have to understand what are their needs, be flexible to accommodate changes, because this is going to happen. It's the traditional project management approach from a cascade to a waterfall versus a continuous improvement cycle. And this iteration should focus on the things that they need in a short term. So with all these lessons learned, we moved to a second phase of the project. That was, instead of creating a network service, we created a network service. So highlighting stressing the service part. And the difference was not about the technology, it was the approach. So the result of this second iteration phase was, instead of focusing on this part, on the technological part, just focus on the abstraction in this one network box. So our management team was focused first now in running in a public cloud platform. So why not just try to fulfill this requirement first? And if you are running in only one platform, the best way to go, instead of using a central point of routing, is just using internal links. So the project today, what tries to fulfill, and it does, and it's in production for this, is because we solved this problem. You have a platform, we're running a lot of different services, networks, and we interconnect them in an abstract way for the user. So the user only has to interact with this one network, and we fulfill this requirement. Next steps. We can also support another platform. Imagine on-premises, creating VLANs or internal routing, or we can support also another public cloud. We can support several services, just implementing a new dependency with this service. And also not leaving the central point to connect everything. This is still in the roadmap. Hopefully our product owner will accept this project for the next quarter. But we will just create a full picture of everything. So the requirement that we get from the users is that this service, network service, should be self-serve, self-onboarding. This means that for a developer, they need to use the network without caring about the details. We create something that the developer is completely autonomous, just to create a service and connect to other services. This connection doesn't happen magically. You have to do a lot of things, but it's the network service task to implement them. Also, in all the cases, what we do for them is choose or decide from themselves which is the best connection that they can get. So they are in one platform, we're going to connect to another platform, they don't care about where this is the other platform, and we decide which is the best connection that they can get, and we implement for them. So everything is self-serve, autonomous, and we also keep monitoring, understanding that the connection is healthy, communicate with them, notify, and provide useful network information. Sometimes we forget that the network has information itself, and we are not communicating to the developers. For instance, probably you are managing net flows or in your network, but are you passing this information to the developers to understand which are the network dependencies on their services? Sometimes not. This is the architecture, quite simple. Basically, are two main services. One is the API is a RESTful API. Everything is implemented in dynamic infrastructure, so you don't have to fear about dynamic infrastructure. We can run this in the cloud, on premises, wherever, but we run this in a dynamic infrastructure, having the coupled infrastructure, that we just implement the API, that is the one that the user interconnects through the load balancer. And the magic happens here, happens in the worker. So the worker is the one that has the dependencies with the libraries, with the different providers, just to implement how we connect, how we run a network service there. So now you can see that the dotted lines means roadmap. Currently, we only support AWS. This is using infrastructure as a service. So we run everything as code. Everything is versioning. Is running in a dynamic infrastructure, so the number of workers scales up and out. Also, it's important to note that we are running in an authenticated service in a single sign-on, so the user has to run this API being authenticated, so we have a secure service. Not everyone can access the service from the company and change things. And also it's interesting to notice, because it was something that I learned when I started this process to become a DevOps, is that the dynamic infrastructure, the monitoring services, either the metrics and events, doesn't have to be pulled from the device. The service itself, the application, should notify to you in a central point that something has started. Because the worker that you have today could be not the same that you have tomorrow. There could be a new deployment process, an escalation that creates a new service that has to be registered, and the old one is going to disappear. If you have to troubleshoot this, you have to know everything that happened all the time. So this is the architecture, quite simple because the project is starting and it's in production from some few time ago. Here we have the entities, just to you realize that this is a project that really works. What we mapped is this concept of a service that is a group of different resources that are the networks that runs in different providers, and finally you create the connection. This is mapped here in the database objects that you can see as a service. Is nothing else than a list of owners. Users then can handle this service. Service has a list of providers. A provider, in this case, in a case of AWS, is defined by the account and the region. And finally, the resource is something that we get automatically. So we scan the resources from you, and we get the subnet, so a list of different subnets, the IDs, layer for filtering. We implement also ACLs in the network. And finally, what you get for the user is you try to establish a connection. And this connection is nothing else than a resource to another resource. And as a user, you don't care about if this is just a link or it's a new route that is published running a routing protocol. So finally, this is the connection that gets the details of the connection, and you can track and monitor this. Everything, as I explained it, is a service. So a service, I don't know how much are you used to create services, but this is just an example of a continuous integration deployment process that we run inside the team just to create this. So it works with a version control system that every developer works in the different features that finally goes through a unit testing integration test that you centralize in a notification process, goes to the code review. So the code is not your code, is the team code. And this code, when it's reviewed by the people, and this is a really good point, because reviewing the code, you learn more than you think. So reviewing what the other does, and also getting the feedback from the others is a good way to learn new things. Not just go to more than 100 comments, but it's a good way to learn. And finally, you still go to a final unit test process and the deployment process. Because at the end, you get a service that is an artifact that goes to a repository of artifacts, and you start the deployment process. So we do everything here in an automated way. You create a new feature, it's reviewed, and it's deployed. So it happens completely transparent for the user, and the user still has access to the service in production all the time. Look here in this acceptance test, because it's what we are going to look in the next slide. The next slide, that is the demo part, is nothing else than the specific end-to-end test that we are using to deal with a new release of this code. When we create a new code, we just deploy this, and we get, at the end of all this process, end-to-end acceptance test. We check that this new release of the service is not broken anything, and if everything is working as expected, we deploy this in production. This demo, it's just 3 minutes. It's running in AWS, and it's a manual process of running the end-to-end test to create, between 2 different accounts, a link in AWS. How it works, basically, this is AWS console. I don't know how familiar you are with it, but you can see that first of all, we deploy with code. We deploy 2 different instances. You can see here that we are deploying stacks. And stacks in this case means that we deploy 2 different networks in 2 accounts with 2 instances, virtual machines, just to check that they can see each other through an internal link. This takes some time, because you have to create all the resources on the public cloud. But eventually, in a few seconds, we will see that now we have here an instance. In this account, we have this instance. In the other account, we will have another instance. Here we are checking that in the routing part of the instance, in the root table, first we have to go to the subnet that this instance is attached to. In the root table, we will see that you have the local route, so your local network, and the internal route. This is what you get by default, before creating the network connection that we are going to create with this service. So once the stack is created, we try in each instance to ping each other with the internal IPs. So we get the public IP, we connect from the SSH terminal, and we create a ping, just to know when the other, you can see here, but at the bottom of this image, what you get is a ping from one instance to the other, just to wait until all the service runs. So what you are doing here is in the global network service, you create these assets, basically 2 different services, 2 different providers. Automatically, the service connects to your provider. We have the rights to do that. And we discover 2 different resources, 2 different VPCs. And now starts the process. What we are doing here is that we create now a connection. And the connection takes some time to be established. You have to think that what we are doing here is not only creating the connection. This is something that you can do in the console. We are doing it through an API, interacting with AWS. But the cool thing for the developer is that we are not only taking care of the link. We are also taking care of the root table and also taking care of the security groups. So finally, when the connection is created, you have seen here the ping. We are going to see again. But what you get is a new connection. And the difference for the user is in the root table. Eventually here, when we refresh, you see that we have added a root table with the route and the link. So you can see here that we can ping each other with an internal link, and the test verifies that this happens as expected. This is a way for the developer to get a running connection without caring about any detail. And also, the same way that you create a new connection, you can delete a connection. So we just delete everything and keep the scenario completely clean. For the user, this is something that they have a service that takes care of everything in the network, so they can just develop business logic, add value to the business, and we can focus on these things. Why our developers use it? I don't say like it, but just they use it. And they use it because we take care of the underlying details. So for them, it doesn't make sense to learn about real networking or root tables. They only have something that works. And this works means that we also take care of get the best connection. The best connection is the cheapest one, the most performant one, and also sometimes you have restrictions about how many links you can get. If we get a limitation on this, we create a new kind of connection. We give them one API. They love APIs. They need to have an API to interact. And we create that only one API to all the different platform services. We keep them notified about connection health. So periodically, we are running a watchdog that checks that the connection is still established, the root table is as we expect to be, and if there are any change, we report a notification to them. Finally, what they get is a out-of-the-box solution to run over multiple platforms. Everything is simple for them. And they get this extra value that is information about the network, what's happening behind. So it's just not the code with the library dependencies. They really understand that the service is talking with other services. So to wrap up this session, takeaways that I take through this process that was around 4 months to create a minimum viable product. It was created by mainly 2 engineers. Lately, more people has come to the team, more software engineer oriented, and they are refactoring everything, but the idea is just the same, create something that handles the network for you. So I will recommend to everyone here in the room, as a traditional network engineer that want to move to a more automated way of doing things, a DevOps approach, don't be afraid of doing this step. I did this 3 years ago. It took some time, some effort, but it was really worthy for me. Also, you should learn some kind of coding. I'm not saying that you have to become a software engineer, but something coding will you make able to join pieces, because it doesn't matter if you buy an out-of-the-box solution from a big vendor. At the end, you have to do some kind of glue between the different pieces, and you have to learn about coding. And adopting this approach, I can say that will speed up the business and also your career, because you get more skills. And don't forget this. Networking is still a key IT skill, but we should be able to bring it close to the business. And that's all for my side. Thanks for your attention. And I leave here you just a link that I have done just to list some of the learning materials, blogs about networking, about Linux networking, DevOps practices that I have been going through during these last 2 years. So thank you very much.
Thank you, Christian. We're running a little bit tight for time, but we have time for one very quick question for Christian, if there is any. Otherwise, maybe catch him in the lunch break. Does anyone have a question? A quick one now? No? Okay. Thanks very much, Christian. Okay.
Thank you.
Yeah, you can just put it down there. So the second speaker of the session, the morning session, will be Peter Lundqvist, who is a systems engineer at Arista Networks, where he works with design and building large-scale data centers. Before joining Arista, he worked at Juniper Networks and Cisco Systems, and he focused on routing and quality of service. And today's presentation is bandwidth and path. So please join me in welcoming to the stage Peter. Thank you. Thanks.
Right. Good morning, good evening, good afternoon, or whatever you're supposed to say. I got strong pointed out from LM that I'm not supposed to do any commercial things here, only one thing, and that is that I have my whole Swedish team is here. So Patrick and Johan, can you stand up? So if there are any, very difficult questions here, these are the guys who can answer, not me, because I'm the manager. All right. So this is sort of a topic on it. I'm not going to ditch too much into the MPLS. I'm not going to teach too much into IP version 4 because, if you not say anything about IP version 6 in this crowd, I guess you get beat up in the yard. What I'm going to talk about is how you're going to adapt path and bandwidth in a large data center. How many people here runs actually a large data center? Raise your hand. Fastly, I know that you run a data center, right? All right. Everything is large, right? This is large, right? Okay. All right, let's go. So based on performance, in a data center or any kind of network, there's a lot of statistics that can be collected. We like S-Flow, but you can run N-Flow or IPFix or any you desire. That statistic can go from mostly any network element in your network. Telemetry, which is sort of the talk of the town, that is statistics that gets from your control plane. That sort of replaces SNMP. Then, of course, you can get all the statistics from your servers, which is the legacy TCP statistics and stuff like that. And in the end, if you want to have something reactive, well, it's logs and alarms. All the way in the network, you can collect these pieces, but you have to do something smart with it. And, the previous sessions was partial about that. Excuse me. So this is a simple output of S-Flow statistics from a single layer 2 switch. Because if you're on an extension, it knows equal amount of IP as an IP router. So you can get all kinds of statistics. So that works with Facebook and Google and all those guys. These are very useful for the east and west traffic, where the servers talk to each other. Then you're interested to see the traffic flow between each host. This is output where you're more interested of the south to north, which is actually traffic going to leave a data center, because then you're interested in what prefix, because those prefixes are tuned to a BGP edge box. So as you can see, there's tons of stats that you can track. How much of volume, who talks to who, and etc. There's no excuse that you don't know what's going on in your data center. What are the possible bottlenecks in a data center? Well, could be leaf and spine. That's a usual thing. You can TCP incast because suddenly mostly every traffic goes to one specific server and not to, despite that you try to load up your application in your whole data center bank, there still are a few servers that get hacked out most of the TCP sessions. You can essentially prove through bandwidth on it here. Bandwidth in a data center is relatively cheap. And if you don't know it, I happily sell you one. BDP Edge is a little bit of a tricky question because that is depending on the peering contract. When you're going to leave your CDN data center, how much can you get from Telia and Tele2 and Telenor and all those guys, right? So it's a little bit depending on the bandwidth there and also how their networks look like, which is sort of out of control, right? You have to rely on their AS path actually is not fooling around with you. So that is a little bit difficult piece to troubleshoot. And then, of course, you have the server, which means that this is a TCP stack, all kinds of data that you have related to your whatever Linux variants and whatever you're running. So all of these pieces are where you can have bottlenecks. And what I will focus mostly is on the path to the BGP edge. So in a data center, the quality is not ping or trace route between servers, right? It's not how you troubleshoot a WAN. Oh, I can reach that server, get along with it. That says nothing, right? The whole quality of a server is based on a TCP statistic. The whole quality of your data center, how TCP behaves in your data center. That's it. Ping and trace doesn't mean a jack shit here. It's all about the statistics from the server. So if you have retransmission, duplicates ACK, and so forth from the server, you need to do something about it. Could be that you have ECMP problem in data center, which is most unlikely. Could be your BGP edge peering, which I'm going to talk a lot of. Could be a DDoS attack. Or it could be this yearly event when Svenska Ridsport gets preset all the time, right? So these are the challenges when you're going to troubleshoot a data center. This is not a lesson about TCP stack. I guess I guess the whole point with it is that everyone assumed that you guys are full flowy with Mikael Abrahamsson's talk about routing header or not routing header IP version 6. I assume that you know your TCP lesson. So I'm not going to try to explain the difference between certain amount of Linux dialect. Some depend more on RTU, others on duplicate action. I just assume that you have read a book about it or talk with someone that knows it. So, but the whole essence is based on this, right? This is from the server, how the performance is. I'm assuming that you actually is interested how TCP works. So there's all kinds of things that you can do. Once those scripts are identified at a certain server doing a lot of duplicate acts, you do need to do something with it. And one of the most common things is that you automatically start a packet capture, because you want to tail down what sessions are in trouble, and thereby you can trace what's the destination of it. So this is one example of it. You can see that you have pretty much duplicate acts for more or less what you send, right? Which means that you have retransmissions. What to do about it? So after a lot of troubleshooting, you decide to swap your BTP edge, and then your duplicates going down to levels that you expected. So these are the stuff from the server that you see actually reactional change. So what I will talk about is the difference between this picture and that with regards to the BTP edge, what they actually have done to solve it. First, bandwidth control. So it's pretty easy actually to build a good data center. You have your leaf and spine topology. I know there are vendors that have been trying to build circles and collapse backbone or all that stuff. Wish them good luck. It doesn't work. The only thing that works is a leaf spine. Next thing is to be aware of the over-provision. So over-provision is usually based on what you do on your leaf, which is where you connect your servers. So if you have more access ports in the uplink bandwidth, you have over-provision. It's easy as that. So if you don't accept over-provision, that is something that you need to do. And again, there's no excuses for that. There are most switch vendors that can supply you where uplinks can match your access ports. That means that the over-provision from the start, you can figure out all about that. The third pillar here is buffers. I come from the routing side before I jump into data centers, so buffer for me is sort of self-explainable. I know that others try to say you don't need buffer. We do magical hacks where we prioritize SYN and all kinds of things. The only result with that is that you have lots of equal bad sessions, right? The only thing to solve and guarantee performance is buffers. So Netnod here, for instance, their server, they will never run anything if they didn't have buffers, because buffers is the name of the game. Sorry about that. I constantly have this picture when I run it. It is essentially, this is how it goes. You build a leaf spine, and you route. Essentially, there are three things to learn in a leaf spine. You route, and you route, and you route. Or you route. That's it. Everything works with the IP. Everything works with routing. Nothing works with more than 3 nodes and triangle if it's layer 2. That's a fact. Second pillar is ECMP. ECMP has nothing to do with bandwidth, really. ECMP is redundancy. Because if you have a setup, it means that you have active-passive. Your passive will never survive once you need it. With a leaf spine in an ECMP, you know that it works because you're using it all the time. So if you're building it in layers with ECMP, you know that your convergence will be that. You're not just wishing that, okay, if I switch into my alternative path, maybe it works. So ECMP is redundancy in a large data center. Right. So why do you need path control if you have this well-designed leaf and spine? It's a BTP edge, because there the bandwidth is costly. That's where you connect your peering, because that's what traffic is going to go out of the data center. So that is where you need most of the tuning. Not really in the east and west traffic. That's very deterministic. You can throw as much bandwidth on it as you want. So let's say that you listen to my advice, you route, and using a protocol that always makes sense, which is sort of BGP. So what is BGP bandwidth aware? No, you pick a path. Has really nothing to do with bandwidth. All right? you turn on ECMP. Is it still bandwidth aware? No, it's path aware, right? It doesn't have any knowledge and differentiation if you have a 100 gig or a 10 gig in the exchange traffic. It simply doesn't know. All it does is that it has equal amount of cost to reaching that destination. So you can play with more specific routes, which means that, okay, I'm going to load balance in transit because I have the same speed. But for my private peering, I will select the ones that have bigger pipes or smaller AS path or whatever. But it's still not bandwidth aware. You can also do more advanced stuff, which means that you bring in all those statistics that I was talking about, measuring, and you try to balancing your source node traffic by injecting longer prefix routes. You artificially create something like third-party next stop. And that means that by constantly balancing network, you maybe can go full utilization. The last advice here is actually invade something to BTP that calls weights. That is that you have bandwidth as a topic, as a BTP attribute that you advertise down to your leaves. So in this example, that is that you have a community for my 10 gig private connection and another community for my 100 gig connection, and I advertise down south into my data center. And this is the well-known community. Based on this, the leaf can then proportion flows, which is 10 times more flows, 10 times more session in the hash goes to the one that has more bandwidth. Now you have at least your chance to balance based on how your BTP edge looks like. Is this a standard? Yeah. I've been working in Cisco and Juniper and Arista, so I guess I've spent my whole career trying to make your life miserable. But all of these vendors have BMD community, which means that I see that as a standard, right? Then, what each vendor do to infect your flows locally, that is vendor dependent. That's up to you to find out. Right, now we're talking about bandwidth, now we're going to go into path. Source routing is destination routing. All I've been talking so far is based on destination routing. But if you have the previous problem I showed you where I need to swap the BGP edge and also the path to it, then I need to bypass how the routing looks like in my data center or in my network. And that is source routing. I guess showing our IPv4 header here makes half of the people that are v6 geeks here not happy, but there's a header in IPv4 that allows doing source routing. I've never seen anyone really using it. So if anyone has used this, I would likely take a picture of it outside and document it. IPv6 has all the capabilities of doing it, right? Because it's just called next header. But that sort of has an extendable security flow. So I guess someone will take me to school here, but honestly, I don't know any Linux implementation that has to turn on by default. So that path also is sort of a challenge. So what to do then if I have an IP network and I want to control my paths? In v4, we'll talk about this sort of a 40-byte header, which means roughly somewhere between 8 or 9 hops, which is pretty good. In v6, you could do more as like, but this is a dead end. I don't know anyone that's using it, particularly not in a data center, based on just an IP packet. Not even Peter Löfberg will try to do this, right? So what to do? So this is an example of a very cloud player, where it's not just a 2-tier or 1-tier. It's not just a leaf and spine, right? There's a whole bunch of leaf spine connected by a super board and a whole bunch of BTP edge. So what they need here is to balance the traffic between the planes. That's the path control. By the way, this picture I got from Peter Löfberg, actually, it's one of his famous ones. MPLS sort of supposed to be the answer to everything. And one of that protocol that really is the most implemented one is, before that, it's going to take the action. Is anyone here that doesn't know the MPLS push and swap action? No, you know it, right? Of course you do. So RSVP. How many in here have an RSVP network? Nordinet, do you have RSVP? Yes. Oh, jeez. All right. You have my apologies. I hope I haven't convinced you to doing that. All right. He's doing a job at the cost of extremely resourcing heavy. It's a protocol designed 30 years ago for having between voice controllers and RTP packets and signaling and stuff like that. So in 2019, try to do something better. And one thing of that is segment routing. And I just had a discussion in the hallway here that segment routing is link state. No, has nothing to do with ISIS, OSPF, or BGP. Segment routing is the concept of doing it. What segment routing is that you have a SID, and that see this as you define your network. You have a network, you have a management addressing space. See that's a label range. And then you have an SID. See that's a loopback, right? Am I still allowed to have 128 in a V6 network, Mikael? Or should I have 64 for that? Or yes. All right. Thank you. All right. I will still use 127 on links, so it doesn't matter what you guys are saying. All right, whatever. So the good thing with it is that essentially it's an IP network, right? It's using IP protocols like ISIS, OSPF, or BGP to advertise segment. And a segment is unique, like an IP address. So if the destination is one IP address, the destination will be that SID. So the SID is unique in the network. But there's no need for any advertisement of labels in between. So you take away all those LDP and RSV riffraff, where you're typing something and you get a 4 or 5 A4 pages long about all the labels you have in your network. So let's see how it works. Also, one thing with segment routing is that it does ECMP. That is why we that build large data center likes it. RSVP doesn't do ECMP. It does a path. So if your routing is ECMP, segment routing will be ECMP. So how many in here knows in depth about ISIS? Raise your hand. So segment route is just yet another TLV in the ISIS protocol. So you get a range, and your prefix SID is sort of your loopback. Now we have created a labeling path, and the awareness of your segment routing will be like awareness of routes in ISIS network. Surely, Peter, you would like this, right? This is labels, but using an IP protocol. You can't have nothing against this. There's absolutely nothing, right? There's no LDP. There's no RSVP. There's ISIS there that just advertise a range. Say yes now, right? He says yes. So now everyone in the community is allowed to have a segment routing. The way to tune the path, we're using BGP, of course. So BGP LU. So BGP LU then sets a stacked path. Then you can tell, in order to go this direction, use these labels, and thereby you will take it that direction. And again, Peter, you can have nothing against this, right? It's BGP that advertise just an IP to a tag, right? He smiles, looks good. So, and also, since I've been doing mostly data centers, we don't really do link state protocols in those, right? We just do BGP. So you can replace ISIS with BGP SR, which means that you only, on your link-to-link BGP peering, you advertise these segments. Surely this is way better than doing RSVP protocol, I think. And Peter also, by the way. So it's the same thing. In the forwarded table, you will have an IP, and you have a segment. You can call it label if you want, but I prefer to call it segment. Right, 10 minutes to go. Is it lunch the next session, or is it another speaker? Another speaker, right. I will hold my 10 minutes then. Else I get kicked out. So there's various ways of doing it, right? You can have those dynamics called protocol to change the path to the BGP, or you can do it statically. So many of those cloud vendors, they run BGP all the way down to the servers, and from the server, they inject this label. And I guess they don't need a fancy ISIs, but BGP-LU they have nothing against, right? So this is one way of doing it, which is, by the way, Fastly is doing. So I think David Barossi is somewhere down there. He's a bird and ponytail, and well, he looks like how internet geeks supposed to look like, no, not like me, right? The other alternative one is that you're using the dynamics on the protocol, which means that your data center is maybe also connected to DCI, so it also is an operator network or something like that. Then you start the whole thing from the leaf, right? And then you're using BGP-LU to change the path. But here you have your ride on the dynamics on the routing protocol. So there's two ways of doing it. So let me very shortly show you two examples. Consider this network. I didn't have time to swap those V4 addresses to V6, but I will do that next time. We'll just create a label for it. So I'm not going to get smirky questions from the V6 community here. But let's say I have here, the most key part here is I have two BGP exchange points here. One is 1 gig and one is 10 gig. I need to use them both in order to utilize my peering and my north and south network. It doesn't matter if certain links, like in this case, goes down, because the pipes between the BGP boxes is rich, because it's a data center. I have absolutely no problem in just throwing 100 gig links there, right? But the traffic needs to leave both of those data centers. The way to do that is how? If this were just an IP network, the traffic to both of these BGP networks would stop on this device here, right? So if IP packet comes there, it's going to go to that destination. He will not send it up there, right? Everything will go up there, so that peer will not be in use. There's no way you can do that except using a label. So can you guys see it from the back? Patrick? Down? Oh, fuck off. You're not going to get the bonus this year, that's for sure. All right. So first one is the route, right? And then what you can see is I have a link bandwidth. The link bandwidth is something I'm going to explain earlier. We will see it, how we're going to handle the hashing towards the destination. And then they have a BGP next hop, and it is the BGP next hop, the SID, that's going to do all the job. And the way to do it is that I allocate a SID, a label, to those BGP next hops. So when this guy is going to push packets, despite that it now has an architecture, which means that more or less everything traffic should lead just one BGP edge, it's because I do a label, right? So a label is going to push to it. So half of the traffic, according to the hashing, will go to the upper BGP port, and next, all the rest with this sort of 10 times more will go to lower. And the way that this BGP community works is that it's not an exact, you can come up with any funky number you want, right? The only difference here is that one is 10 times more. That means that 10 times more the sessions will go to the one that has higher bandwidth. So now you will utilize both of those BGP edges. And the way to trick it is because the destination here is a segment. It's not just the BGP next hop that's an IP. 55, right? A very common in data center is that you don't run full feed all the way down to the leaf. You can play this trick exactly the same way, but you generate a default route down your network according to those hashing like the BGP community. So this time the result will be exactly the same. A last scenario here is that I want to change the path. Remember when I had issues with duplicate transmissions because my BGP edge needs to change, but I was uncertain if it was the BGP edge or the path to it. So let's change all that. The way to do that is by, for instance, using a controller. So what the controller here is that it changes the path, the BGP next hop, and the labeling out, and it forces, without doing very heavy routing changes, forces the traffic to use only one. And this is also one of the scenarios that can only be done if you're using a label here, and essentially I call it a segment. So what you program down here is a path where this node here he forces him to take this explicit path. So this is as close to RSVP you can go without this funky RSVP reserve and state change. Everything here is done from ISIS or BGP. Right. 5 minutes to go.
Perfect.
Questions?
So we have 5 minutes, so we have some time for some questions for Peter, if anyone dares. Right at the front.
Yeah, sort of expected.
So you forgot the Belgian accent.
All right. Again, I'm in the hallway. I'm the good-looking one. My teammates there, they know everything about segment routing and preferably better. And of course, you can talk to Peter Löper. He's now also a champion. Thank you very much.
Okay, so the final speaker of the session is Kalle Eneroth. He's the Chief Technology Officer at IoT Sweden. He's a computer scientist who primarily works with the ICT market. Over the last 20 years, he has worked at companies such as Teleka, Ericsson, Accenture, and IoT Sweden, building and delivering network management solutions and telecommunication technologies. So please join me with welcome Kalle to the stage. Thank you.
Thank you very much. I think it is safe to start like this. And now for something completely different. But before I do that, I spoke to Britney Spears earlier. She was really pissed off that I had replaced her slot today. For any grievances, I please direct them to Kai Kjellgren, who thought that it was a good idea to talk a little bit about how we connect mass IoT moving forward. Right, so how many knows about, or knows what LPWAN is? Low Power Wide Area Network. Have you heard about LoRa? Narrowband IoT? NB-IoT? Good, okay. Sigfox? All right, good. Then not too many hands, but hopefully you will learn something new today. And I guess the message here is, have no fear. Sigfox is finally here. Sigfox, if we can get this to work. No? Where do I... There we go. My name is Kalle Eneroth. I'm the CTO of the Swedish Sigfox operator. We started 3 years ago by planning and ramping up for a massive rollout, build-out of the global IoT network, which is called Sigfox. Sigfox is this low-power, wide-area, technology-based operator, which is global. It is the world's largest dedicated IoT operator. It's present in 50 countries. It's going to be 60 by the end of this year. Sweden was number 32 for building out the network. And that makes us the largest dedicated IoT operator in Sweden. Today, we cover 60% of the Swedish population, 23.3% of the landmass, and we're growing. We've rolled out so far about 100 radio base stations. And when we're done, approximately a year from now, we're going to have 400 or 450 radio base stations covering the country. Now, it's important to notice here then that the low power wide area technology really enables a new type of market for IoT communication, We're not talking about bandwidth or high data. You don't stream audio or video on this network. You send small pieces of data. With the Sigfox technology, it's up to 12 bytes maximum as payload. But there is a massive demand for this type of communication because it enables certain things through its design that we'll come to a little bit later. Another thing that is also really important to note is that we are an operator. So we sell subscriptions in this network. We build a telco grade, or a carrier grade network by placing our antennas on an optimal height in order to pick up as many signals as possible. All of the devices that communicate in this network, like this little bad boy, for example, a GPS, Wi-Fi sniffer, accelerometer, and BLE chip inside, they are all certified formally. And this is a mandatory process that you need to go through in order to be able to commercially communicate in the Sigfox network. So this is done centrally in France at the Sigfox labs. All of this we do to build quality in the network. We build a network for generations. And with this, we can guarantee globally that we have a 99.5 availability where you have the Sigfox coverage. We build for 99.7, but we guarantee commercially 99.5. Another really interesting aspect of this, given that this is a global network, there is no roaming. It's one contract, one network, one subscription. So if you buy this one here in Sweden with a Swedish Sigfox subscription, this will work all over the world. Those of you who know a little bit about the ISM band, because this is a sub-gigahertz band. In Europe, parts of Africa and parts of the Middle East, it's the 868 megahertz bandwidth that we're communicating over. This is a military frequency in the US, so you go to jail if you start communicating with that there. So there we use the 902 megahertz instead. In South America and in Asia, we use 920. But there are also solutions to be able to technically determine which network do I belong to right now so that you automatically can switch between these. It's a solution called Monarch within Sigfox. Now, with IoT, it's fantastic. This is really applicable everywhere, in every segment, in every industry. When I started working with this, I couldn't be productive for several weeks because I simply couldn't see the trees because there was a forest standing in the way. What we usually look at when we start looking at these types of solutions are two things. Either you want to optimize your existing operation, your existing processes, and thereby gain cost reductions. Another path to take is to generate new value streams, new values that you can bring to your customers and thereby earn more money on it. Just to take one example, there is a utilities company here in the Nordics that has 2,000 dams. And they have sensors, existing sensors there that measure the pressure of water to determine the level in these dams. They have a GSM modem today that is communicating the data on a regular basis, but it's just small sensor data, so you don't really need, it's a little bit overkill to have a GSM modem for that or communication for that. They need to change the batteries on these modems 2 to 3 times per year. So there's one entrepreneur in the north of Sweden who has really said, no problem, I'll take care of this. I'll do this. All the 2,000 dams and devices all over the Nordic region, I'll take care of that. And it will cost you this much per dam. So they have a cost, this utilities company, of about 1.5 million per year. Right now we're running a pilot where we show that if you put a small Sigfox sensor, you keep the existing sensor, but you just retrofit a new communication path with Sigfox. We can come down to slightly above 2,000 SEK per year, because then you have a battery lifetime of over 10 years. That's those rare moments where you see ka-ching in the eyes of the customer. We have our legacy networks that are really important and are good for various things. If you're going for smart cars, for really mission-critical applications where you need to have real-time data, large volumes, then this is not what you should do. But there are so many municipals or companies or industries that have been wanting to hook up maybe 2 or 3 million devices instead, or objects. Then this is just not good enough. It costs too much. It costs too much to maintain. The devices are too expensive. So the whole idea with LPWAN in general, but Sigfox in particular, is to open up for the mass volume IoT business. And this is going to be a real game changer moving forward. So looking a little bit, taking a comparison then on the 4 main pillars. With Sigfox, we are cost efficient, we're energy efficient, we have a global reach, and we have simplicity. If we compare to the legacy networks, we have LTE, which is really great for streaming video, for example, Wi-Fi, likely so. The Bluetooth and Zigbee, more localized networks, but also really, really good. But they really do not perform on all of these different levels in the same way as an LPWAN network does. And looking a little bit closer to this, we have a really simple solution. Every tag, if we look at something to just track positions of objects, every device has a hex code, 6 positions. It's globally unique. So with this, we're actually moving away from plug and play, because this works right out of the box. You simply just register your code if it hasn't been done already in the factory, and then it works. When I send this to my partners or customers, I give them the dashboard access before I put it to the postal office, and then they can follow it all over the world down to their position. It has the global reach, meaning that with 50 countries and growing, the manufacturers of devices that want to connect them and be able to communicate the data from them, if they choose a technology like Sigfox, they overnight tap into a global market of 50 countries. Again, no roaming. I go to a lot of these different kinds of IoT events, and I hear a lot about different types of industries within logistics, within construction, within e-health, and they all say the same thing. When they present their pain points, they really almost literally describe the whole point with low power wide area network and Sigfox. Energy efficiency and low cost, not only for the traffic, but also for the actual devices. This tracker costs a little bit dependent on volume and what technology is in it, from maybe 250 Swedish crowns to 500. It wasn't that long ago that a GPS cost more than 2,000. Depending on the battery life, this one, again, this is completely closed in plastic. And with the small battery that you have in this one, you can send 14,000 messages. So if you do the math on saying a couple of messages per day, you see that it's several years of runtime on this battery. We're really seeing that the floodgates are opening now. The market is, since this touches on all markets, the maturity level is very different between the different verticals, but it's really something that is happening now. We have an institute here, the Machina Research, who estimates that in million number of low power wide area connections, we're going to end up here by 2024. Right, so let's look a little bit about how it works. I'm actually not going to get that much into technical details, but I'll be here all day. So if you're curious, then come and grab me in the coffee break and I'll explain a little bit more. So basically, we have your sensors, your trackers, whatever it is that is sending the data. They're sending it to our networks, our base stations. We are backhauling them to a back-end system centrally for the entire global network, located in France in various locations. There, it's pushed out, either pushed out or pulled to a target system of the customers. So basically what we do, we just transport the data. It's a two-way transport, and it's important to point out here that two-way with a bit of a modification. In order to save, primarily, in order to save energy, you want this device to do as little as possible over the course of its life. So when it comes to the downlink, I mean, it sends data when it wants. But when it comes to the downlink, the device itself sets a flag saying, I will now listen for 30 seconds for something that the network wants to tell me. That's the downlink. This would typically then mean that you can get configuration changes, new pieces of information that the device needs to operate in the fashion that you want. It's up to 12 bytes only, the payload, in uplink. In downlink, it's only 8 bytes. And due to the fact that we are communicating over the 868 megahertz ISM band, Industry, Science, and Medical, there are regulations in all parts of the world. For the EU directive, it says that you're only allowed to use 1% of the duty cycle. So that means that we will only be able to send one message every 10 minutes. A message is always sent 3 times, 2 seconds per message. So if you break 1 hour down into 3,600 seconds, 1% of that is 36, and there you have your 6 messages in an hour. For the downlink, you're only allowed to have 4 messages to the downlink. So this one, for example, when it wants to get a position at a predetermined regularity, then once per day this one sends, okay, should I change my default 4-hour interval to something else? If yes, then we have configured that, and then every 24 hours you will be able to make a change. Everything in the design of this technology has been focusing on lightweight when it comes to energy consumption. I don't need to tell you guys that an IP header is 40 bytes. For the Sigfox communication protocol, it's 14. I mean, with IP, it doesn't matter, because if you're sending more than a kilobyte in data, the overhead is really relatively small. But since our payload is up to 12 bytes, we have to have really small bandwidth. If you're looking at other more cellular technologies, like narrowband IoT, for example, they are also very energy efficient, but there is a slight challenge with the fact that they need to go out and negotiate for a communication path. They need the throttle in the network. So there's a lot of signaling traffic that goes on, which obviously then eats up a lot of energy. So all of this we do in order to prolong the battery capacity of the devices. Again, remember the dams. This is really something that constitutes a serious cost business-wise. So 12 bytes. What can you fit there? Well, one GPS position is 6 bytes, so you can fit 2 of them. Or you can come up with something smart that you only take a delta position or something so that you can fit more than just one. You can also do 6 measurements of temperature between -200 and +200 degrees, for example. Or maybe something else like a speedometer or CO2 levels or whatever you might want to do. Maybe you just want to determine if something is open or closed, 1 or 0. Then you have 96 positions all of a sudden within one message. And then, very common and very useful, just sending a small ping. saying that in an alarm situation, for example, where you want to put this on a work shed that no one ever uses, but you want to have it covered for 10 years, you need to make sure that this guy has it under control. So every 24 hours it sends just an empty message saying, don't worry, I've got it under control. So why do we do this? Well, you shouldn't send more data than you have to in order to, again, save energy. Right. If you start looking at IT, you will quite soon you will get into discussions around ecosystem. So what is an ecosystem then? Well, it's everybody who makes part of making this work. It's the chip and module vendors, both for sensors but also for connectivity. It's the device makers that takes these chips, puts it on a board in a nice casing with the right proper antenna, and then sells it as a solution. You've got the connectivity providers, the likes of us, the likes of you guys building the backhaul that we are communicating over. The platform providers, the ones who are doing the AI, the data analysis, the machine learning, the presentation of the data into an operator, what comes out on the other side of the Sigfox network, in our case. And then you've got the vertical application. You've got the e-health people, the smart city, the ones who are really, really experts on their niche, their vertical. I'm a strong believer in that there is no one company that can provide this, the whole echo chain. There's no one player that can do this. There are a few foolish attempts from some companies, like my previous employer, Ericsson, loves to be all of that. But what I see now in the market is that we really need to find new, smart ways of working together. When I'm looking into this, I don't have time to copy what others are doing. There are so much new stuff to do. So if a customer comes to me and asks me, I want to do this, then I know, you do that. So then let's go together and we have a smart partnership instead, so that we can focus on doing what we know that we are good at. And with the fact, again, then, that it is such a wide market, and it's been around for 8-9 years, it has had time to grow. There are almost 1,000 commercially ready solutions, end-to-end, communicating over the Sigfox network. And we're not talking about small players here. Just a few weeks ago, it was announced a partnership between Sigfox and Bosch Siemens. So by the end of this year, all of the Bosch Siemens equipment that comes out of the factories is going to be Sigfox enabled. Also with one of the largest companies, Verisure, has their home alarms connected via Sigfox. And there's much more coming. Just in January, a 300 million euro deal was struck with the government of China in order to build e-health solutions in larger cities in China. And then that means that the network is now going to be built also in China. And that, of course, will be a catalyst for the entire ecosystem in building new and cheaper devices constantly. So just to take a few examples. Like I said, Verisure. This is the Verisure home alarm system. It's one of Sigfox's larger customers. They have about 1.52 million subscriptions, something, in the network. They have as their first line of defense the local IP network. However, it's very easy to just cut that cord, or maybe the customer themselves do that for the burglar when they go on vacation, for example. The second one is an autonomous GSM modem. You can get equipment for 100 euros on AliExpress. Well, 100 euros plus 75 crowns these days. But to just jam that out. Third line of defense, Sigfox. Since every message in Sigfox is sent 3 times, and it's also randomly spread out over the band, bandwidth that we have, or the spectra that we're operating within. It takes a tremendous amount of energy in order to jam this. The way that we actually won this deal was that Verisure themselves, they placed all of the jamming equipment that they had in their own labs around the conference room. They started it, and then we have one of these big buttons that first blinks red until the message goes out and comes back, and it becomes green. If we press this and it becomes green, we sign the contract. Those 13 seconds, I think, that it took to come around was quite nervous, but eventually it turned green and we got the deal. A second really interesting case, and this is the fun part. I mean, I'm a computer scientist. Who knew that I would start working with trains, with home alarms? You can't imagine how poorly the wagons pulled by trains are monitored today. We actually found a farmer in the south of Sweden on a stick track somewhere, forgotten, who had 2 of these wagons. And he used it for storing his firewood. And these are several million each in value. Anyway, so trains running around Europe are now monitored with similar devices like this one. Every device, almost every device that has a tracking function has this accelerometer. Naturally, because since we're chasing energy here, we don't want to send data when we don't have to. So if this one lies still, you shouldn't be communicating with it. So you only want to send a new GPS position when it's in movement, right? So the accelerometer is really important. Now the thing is that this was great. They really got a good logistical flow. They saw where their carts, their trains were at all times. But they also found something else that they had not accounted with. And that was, in certain places, whenever a train went by, every cart that had one of these gave an extra bump from the accelerometer. So they got some service engineers out to these points, and yeah, of course, there was something wrong with the tracks, something that needed fixing. And you can imagine then the value just from finding that information without having to search for it yourself. So a lot of various side effects. Another industry, cows, connected cows. We have a bracelet that we put around the neck of cows. And the idea here is that every 21 days, the cow is in heat. So in order to get calves, she needs to meet then a bull, but, well, these days it's more a veterinarian, I guess. But you have 14, 15 hours of window to make this happen. Then obviously, if you have a stock of, I don't know, a couple of thousand of animals, it will be very difficult to keep track on that. At the same time, you can also measure certain vitality measurements like temperature and things like that to make sure that your animals are okay. But it's not that gives you the indication of when it's time for the vet to jump in. It is the movement of the cow. It moves in a certain pattern, which we can determine with this tracker. And that is how you know that it's time. Another prestigious project for Sigfox, and this was one of the early ones, was rhinos in a national park in Kenya, where they had tremendous problems with poachers who were killing these animals, illegally, of course. So they put, again, a similar type of tracker where you could see the location of the animal. Animals, they often run around together, and you could also measure the stress level of the animal. And when these two gave the right combination of indications, you could send out the security people out there. In the best case, you would actually be able to detain the poachers who were there. In the worst case, at least you managed to save the lives of the animals, most likely. It was very successful. Again, not a mass volume, but it really illustrates a very good point of this type of technology. Anyone like beer? A beer never tastes as good as if it has been monitored by Sigfox communication. In Spain, in France, in Portugal, every beer from tap is actually, with very few exceptions, is actually monitored via Sigfox connectivity. What they do, they measure the levels in the kegs, but also the temperature in order to have the control and quality of it. I'm actually a trained sommelier these days. I got a golden ticket from Ericsson once, and I managed to jump on a sommelier training. So I'm a little bit more into wine. And there is this company, it's two guys who exited NASA. And they're operating from Silicon Valley and from Linköping here in Sweden. And they have a very nifty solution. They have sensors that measure various environmental climates in the ground. They have low-flying drones collecting data, and then they take satellite imagery on which they build a three-dimensional topology view. Then they build an information cube so that they can then make certain decisions informed on how to progress with the production in order to maintain the quality, but also perhaps the character of the product. They are working with agriculture in general, but with wine production in particular. And no wonder, because I don't know if you've heard this, but within a vineyard, from here to there, it could actually be two massive differences in the microclimate. And this is tremendously important if you want to really keep producing that character, to have that under control. So they have about 4 pilots now around in Portugal, in Hungary, in Turkey, and some other country. But also, of course, they are monitoring the Swedish strawberries that are being produced outside of Nyköping. Right, so just a reminder then on the importance of this new type of technology. We have the energy efficiency. Priority 1. Closely after that, you have your cost efficiency, both on the device side, but also on the connectivity. This is needed for mass IoT, mass volume IoT. Then the simplicity. It needs to be simple to apply this. And then finally, we've got the global reach. This really works seamlessly over the entire world where you have the coverage. Thank you.
Okay, hands going straight up in the middle there. Sorry.
Mikael Abrahamsson. So how does this scale? Can we have hundreds of millions of sensors in the Stockholm area?
Yes.
Can they sit in the basement where there is normally not even mobile coverage?
Yes.
Okay. With your current rollout, or do you need to do more?
No, what we're doing is that we are... we have had a strategy where we have built an umbrella coverage, first of all. We want to cover as large parts of the population where they are and where they move, because that's where we see the initial business. Like I said, we've built about 100 base stations now. Last fall, and we've done that in a little bit over a year. We've built this coverage. So what we had started doing, we met with a critical point or critical mass in terms of land coverage, where we also started in parallel to densify. So we are currently now densifying the network. We're working closely with Terracom, using their secure sites for this to also get the carrier grade type of network up. When we are done, most parts of Sweden will be covered with at least 3 base stations. And when you have that good coverage, what you will see is what we call the deep indoor coverage. Since we are working on a sub-gigahertz frequency, you have a very good penetration. So we actually can come down to 2 stories underground, 2 floors underground with the technology, if you are close enough to a base station. But most places will be.
Okay. And when I said hundreds of millions of sensors, is this sensor sending 1 message per day or 2 per year, or is that actually something that talks hourly?
No. The limitation here is 140 messages per every 24 hours.
Per device?
Per device, per radio unit.
Okay, so you could have 100 million devices in Sweden, or let's say in Stockholm, 100 million devices sending hourly messages.
Yes.
Okay.
Absolutely. And also on that note, every base station can actually handle several million of messages within the same time frame. Just to comment also a little bit on this, My mother-in-law was visiting last summer, so I went to Helsinki and I chose to take the boat instead of the flight because I wanted to prolong the trip. Anyway, I was sitting there. I was meeting with one of our partners, Tieto, and I was sitting early in the morning, started preparing my presentations. I was in the middle of the Baltic Sea, just between Stockholm and Helsinki. And I took out my field tester that I always carry with me, and I checked. Oh, shit. We've got minus 112 dBm. That's really good coverage. We can pick up signals down to minus 145. So I took out my phone and I took a picture of this to send to my colleagues here in Stockholm. And then, okay. I had to wait for 3 hours in order to get GSM coverage in order to send the text. So it's really potent. Sorry, more questions.
Okay, we had one at the front, and we'll have one from Marco, quick one, and then front, and then we have to break for lunch, I'm afraid. So Marco first.
I'm not sure whether it's a quick one, but in line with what Michael said, and the big elephant in the room is kind of decommissioning. We're now looking at self-harvesting devices that might ping forever. What is Sigfox strategy to ever get these devices back? Or is it basically just toss them in the field and they will be beeping for the next 100 years?
Yeah, I see. Because one of the things that we are looking at, I mean, you want to choose, of course, your applications soundly so that it brings a value and does not impose any threats in any way. For example, what we are looking a lot at right now is disposable devices that can be biologically taken care of just by throwing them away. So zinc batteries is a really hot topic right now. I myself am looking a lot at these one-use tags, just a sticker that you put on a box and you can track it then all over the world. I also, there is also a triangulation possibility between the Sigfox networks also to get a rough position of where an object is. But sure, sustainability is really high on this topic, but I think that we can really, with this technology, save a lot of resources. Yes?
Okay, last question at the front.
So you're sending pretty short messages, and so how do you sign the messages? How do I know that the right cow is sending the message and it's not the hacker?
Yeah, okay. First of all, everything is encrypted. So you have a unique encryption key in the device that only the manufacturer has. Then the fact also that the device itself determines when to listen. Oh, okay, so you mean the uplink data? Yes. Yeah.
Yes.
Yeah, but that's the encryption. And the device IDs is something that only the owner of the solution has. So the network will not accept anything that is not from that particular device.
How about a replay attack?
Yeah, sure. I mean, nothing is perfect. I should really not say this. I was just about to say the network has not been hacked yet. That's like inviting people for it.
What is your door prize?
Sorry?
I feel that the alarm company people were incompetent, right? So.
No, but if you look at other technologies such as for example 6LoWPAN, which is another LP WAN player.
You're changing subject.
No. They have IP all the way out to the device. We don't.
Okay, but I asked sort of so how big was the address? You said 6 bytes or 6 hex?
It's actually 8 hex. It's a hex code of 8
so
positions.
It's 8 4 bits?
Today only 6 hexa characters are used.
So there are 8 4-bit slices, so it's 4 bytes.
Yeah. No. It's a hexa. Yeah, sure. Okay, sorry. Yes.
Hex is 4 bits.
Yes, exactly. Yeah.
How many bits is the address?
Sorry.
How many bits is the device address?
The address it's then 4 times 8.
4 times 8. That doesn't make 100 million.
Exactly.
All right. I'll email you the answer to that.
Okay, I'm afraid we've reached the end of the session. Could you please join me in thanking Kalle for a very interesting presentation? I suggest we take a very well-deserved lunch break, and we'll see you back here at 1:30. Thank you very much.